So we are going to cover logic, and logic is extremely important let's see if it hurts us. Okay. Anyway, so logic is extremely important for two reasons in AI. One of them is a philosophical reason, and one of them is a practical reason, as well as a philosophical reason. So let me talk about the very simple practical reason, because it's actually something that we have already understood so far. The practical reason is that it's a very expressive representation, not very natural and intuitive, but very expressive. Satisfiability problem, for example, is an NP-hard problem. It's one of the first NP-hard problems that you study, or NP-complete problem when you study satisfiability. So now, by thinking about how to solve an NP-complete problem and coming up with a good solution for it, it's an NP-complete, but good solution, works in practice kind of a solution, we allow a large class of problems to be solved using these techniques. And similarly, the same was true in CSPs, by the way, that we did last week. But they're not as popular, but the same is true for them, that it's an expressive representation. You can convert a lot of your problems into CSPs, solve them using constraint CSP solvers, or the techniques that we have learned. What is going to happen even better in SAT is that we have some excellent SAT solvers. Incredible amount of progress has happened over the last years in SAT solvers. So that will be your assignment also, to take something random, a very different problem, nothing to do with SAT, convert it into SAT, and see how the SAT solvers are able to solve it. Okay? So that's the practical reason why you want to study logic. By converting it into a satisfiability problem, and by making use of the solvers that are present, you will be able to solve complex problems, all NP-complete problems, or even sometimes hard. Now let's talk about the philosophical reason. I think that's very interesting. So far we have been saying that what is fundamental to intelligence is to solve a problem. Give me a problem, and an intelligent being, an intelligent machine will be able to solve that problem. And so we have learned some methods on how to solve these problems using search as the fundamental paradigm. Another important aspect of an intelligent being, or sort of a necessary but not sufficient aspect of an intelligent being, is to be able to reason with information. See, you cannot ask a 3-year-old baby to do addition, or 2-year-old baby to do addition. They haven't learned the concept of numbers yet. Once they understand the concept of numbers, then you can teach them the concept of addition, and so on and so forth. In a very same way, your agent cannot start with a blank slate. Suppose you want to make an intelligent diagnosis engine, intelligent doctor, or what have you. You cannot say, okay, you are a doctor, now you treat me, or give me suggestions on what medicines should I take. Of course not. You have to start with some background, you have to start with some knowledge, you have to tell them, you have to teach them, or teach the agent, what kind of diseases are there, what kind of medicines have been used in various diseases, and so on and so forth. You start with some background corpus, some background knowledge, and then you can ask the agent to make inferences based on this knowledge and reason, and go further and show intelligent behavior. So a fundamental aspect of all of this process is to be able to reason with information, reason with knowledge. Start with some knowledge base, start with some starting point which is not a blank slate, and then use this knowledge in drawing conclusions that will be helpful in its actions later down the line. That is this whole area of knowledge representation and reasoning. This is definitely not going to work. Let's try again. Good. So the area of knowledge representation and reasoning says that you have to somehow give the knowledge to the agent. You have to tell the knowledge to the agent, one way or the other. How do you tell that knowledge? And how do you make that agent use that knowledge to draw more conclusions? The field that studies all of this is called knowledge representation. And again, I will stress that CSPs is also another way to represent knowledge. That these are my variables, these are the allowed values, these are the constraints, something we did last time, is also another way of expressing knowledge or representing knowledge. Often people don't think of it that way, but it is. Logic is sort of the fundamental starting point when people start to think about knowledge representation, right from the 50s and 60s. I don't know if you remember in the introduction, Alan Newell and Herbert Simon, CMU, were trying to see that I want to make a theorem prover, because if I can make a theorem prover, then I will be able to show intelligence, and I want to prove all the theorems that Bertrand Russell talked about in Principia Mathematica. So they had that goal. So they knew that proving theorems or starting from some assertions and proving new assertions is a fundamental aspect of intelligence. But that starting from some assertions is the knowledge part, and proving new assertions is the reasoning part. So how would you represent knowledge was the first question, or one of the first questions that people in AI had to be thinking about. And the first solution that they came up with then was to use the logic, the framework of logic, which we have had forever, right? From Greek philosophers and so on and so forth. So that is the goal, and so logic is extremely important in design of intelligent agent because of that. In fact, the history goes like this. Logic became so fundamental in AI that pretty much nothing was conceivable without it for a long time. So people were discovering techniques to make logic work and to make theorem proving work and so on, so on, so on. And at some point, history goes that they realize that it is not working, and there are reasons why it is not working, which we'll get to when we get to probability. The reason is, although the world is deterministic, everything is deterministic, or the model of determinism is so difficult that there are so many exceptions all around that you cannot encode everything. So you cannot say that I toss a coin. It's technically, given the air pressure and the speed with which you toss the coin and the weight of the coin and everything and the number of flips, you know exactly whether it's going to be head or tail. But modeling that process never works. A much easier way to model this is to say, okay, we have a coin and the probability will be half. It's a fair approximation. So what happened by constantly modeling it into logic, which is brittle because it is only allowing determinism in the world and there's only so much that you can do with it, we were not making progress because we were not able to handle exceptions very well. Exceptions or uncertainty. And therefore, around the 90s, there was a massive shift to the other side of AI, which is what I call the modern AI, into probability. That we need to handle uncertainty. And now the buzzword is not even probability; it is more combining logic and probability together. That we would not get to cover, but this is what the last 10 years of research or 12 years of research has sort of gotten us. A lot of people are working on getting logic and probability together.
Not even with the extra class?
Probably not with the extra class. Okay. You should make a list of things that you want me to cover, and if you really do extra class, then I could try and pick one or two of those. Alright, so coming back. So the idea of knowledge representation is that we want to represent the knowledge about the world in a manner that facilitates inferencing, that is drawing conclusions from knowledge. And here is an example. Okay, so I am introducing one other concept here, because intuitively, and the concept is world. So, there would be a representation of what is the reality, and that is knowledge representation, right? So the reality is the world that we are living in, and the representation would be some kind of symbols that will be used to represent the world that we are living in. So let's take an example. This is a very simple example of arithmetic logic. Arithmetic logic is the logic of numbers, let us suppose. So x greater than or equal to 5. Suppose this is the only thing I know. There is a reality about x, what its value is. that reality is not known to us. But we know that if x is greater than or equal to 5, then x is also greater than or equal to 4. That's a logical conclusion that we can draw based on what we already know. That is the inferencing process. Or x is greater than or equal to 5, that means x square is greater than or equal to 25. We can make these conclusions, number one. Number two, x has some real value, and any knowledge that I have is reducing the set of the worlds that are possible. So imagine there are lots of worlds. In each of the worlds, x has different values. And by knowing that x is greater than or equal to 5, I have removed a lot of the worlds. Now if I tell you x square is greater than or equal to 1000, then you have removed even more words. So with each little bit of information that I give you, with each sentence that I tell you about my world, my knowledge base, you are reducing the set of words that are consistent with that knowledge base. So there is this divide. The logic is the representation of what I know in a symbolic form, and there is an equivalent interpretation of it, the set of words that are consistent with this knowledge base. So far so good? Now, there are many knowledge representation languages. What we will be covering today is the propositional logic. And I think you all know propositional logic. So, does anybody not know Boolean algebra? True, false, and or not. This is exactly what we are going to do today. You could have skipped today's class. No, I'm kidding. But that's it. So this is the goal, right? So in propositional logic, so we will have two commitments in any logic. Actually, more than two commitments, but let's do the two main ones. One of them is the ontological commitment, and one of them is the epistemological commitment. These are just fancy names for simple concepts. So the fancy name for the ontological commitment is that what is my world comprising? What is my world composed of? And in propositional logic, my world is composed of facts, just primitive facts that I will assert. Like x is greater than or equal to 5 is a fact. That's that's the starting point of propositional logic. An epistemological commitment says, what do I know about my ontological concepts? So in this case, facts. So what do I know about my facts in propositional logic? I either know them to be true, or I know them to be false, or I may not know them at all. So they can be both true and false. For example, I know that x is greater than or equal to 5. What can I say about x is greater than or equal to 6? Can't say anything right now. It could be true, it could be false. So it's unknown, right? So this is propositional logic, where facts are either true or false, or I may not know about them completely. Now there is first order logic. And first order logic says that world is not really made of unit facts, it is made of objects and relations between the objects. Think Facebook, it's made up of people and friendship between people. So my fundamental units is not a fact, it is an object, set of objects, a set of relations between them. And now, what do I know about them? Again, true, false, and no. Is X a friend of Y? Is this person a friend of that person? Well, I may know about it. It may be true. I may not know about. I may know that it is not true, or I may not know about it. So the ontological, epistemological commitment hasn't changed, but I am dealing with a much more expressive language now. The syntax is much more expressive. On the other hand, my knowledge about the facts could change. So, for example, I could say that this fact could be true with some degree of belief. Talking about Seattle. Is it going to rain tomorrow?
Yes.
Okay, talking about something else. So that's a probability distribution. So my knowledge about a fact would be that it is true with a certain probability. So now I have taken the same idea of the fact, but extended it in the dimension of what I know about it. And then you can have probabilistic first order logic, which we will not get to talk. But if you're interested in that topic, one of the world's leaders in that area is right in our department, Pedro Domingos. He is famous for Markov logic networks, and by the name you can sort of guess logic because there's logic in it, and Markov, so hopefully there's some uncertainty into it. So he actually is one of the leaders in probabilistic first order logic systems. And so if you're interested, maybe take any course that he teaches next time. Even if it is an intro to Java, he'll definitely talk about Markov logic. I'm just kidding. But you know, he often teaches that, even in intro to AI classes. All right. Now there's a funny logic that we will not cover at all in this course. So I shouldn't call it funny. I should call it fuzzy. So it's called fuzzy logic, and the change that makes is that it says that, see here, there is a notion of a truth and false, and I know it or know it accurately or don't know it. Here there is a notion of truth and false, and I don't know it correctly, but there is a notion. Here the notion is that there is no notion of truth and false. Truth itself is fuzzy. What does that mean? So if I asked you, is that guy tall? What is tall? Tall by itself is not an absolute concept. It's a fuzzy concept. Is it hot? Is it tall? Is he tall? Here's another example which is quite reasonable. I have a box and it has let's say red puppies and brown puppies. And I take a puppy out and look that it is red. That's true, false. The puppy is red. I take the puppy out, but I close my eyes. I don't know it, but the puppy is still red or brown. There are 90% red puppies and 10% brown puppies. I close my eyes, take a puppy out. I can say that the puppy would be either red or brown, and I also have a probability distribution of with what probability the puppy is going to be red. Now suppose the puppy started breeding, and then after some time I take a puppy out. It may happen that I am not able to figure out whether this puppy is red or brown. Maybe this puppy is somewhere in the middle. So is this puppy red or is this puppy brown? Now becomes a fuzzy concept. What is the color of this puppy? It becomes a fuzzy concept. So when we get to the degrees of truth notion, then that is fuzzy logic. And again, it's a dimension that is coming out on the z-axis. So now you can create other combinations like probabilistic fuzzy logics and so on. And then people have added time, so there's temporal logics or linear temporal logics, and there are lots of logics, because logic was the fundamental thing that everybody in AI was studying for a long time. There's just too many logics. There's full notion of non-monotonic logic, which says if I tell you that somebody is a bird, then you start to infer that this X is a bird, then you feel that X is can fly. But now if I can tell you that X is a penguin, then you say, oh, it is not. Why is it called non-monotonic logic? So most logics are monotonic. As I tell you more about something, you only reduce your set of models. But non-monotonic logic says that if I tell you more, it might even increase your set of models or set of possible words. So again, not interesting. Very interesting, but not for this class. So there is a full area, is the point. Okay. So yeah, so as I was saying, there are a lot of these languages, and there's ontology languages. We work with natural language processing. You have to deal with ontologies, semantic networks. This is Bayesian networks that we will cover. But for the traditional logic and chaos systems, we are only going to cover propositional logic, which is the topic for today. And I think by now I have gotten home the point, hopefully, that the point of logic is that by starting with true assumptions, you can deduce two conclusions, and that's what we are going to focus on. Now, I am not going to be talking about truth and what it means, right? There are lots of funny, interesting quotes about truth. Philosophers have been thinking about what is truth. You know, if you really start to believe that beauty is truth, and then add to the knowledge that the beauty lies in the eyes of beer holder, then you can start to make lots of interesting assertions and conclusions. But we will not get there. That joke was lost on you. so let's keep going. So let's start with the technical content. So what are the basic units of any knowledge representation system? It has to have some syntax. And you are programming, you're a computer science student, so you understand what syntax means. But let's still make sure that the definition is clear. It defines what sentences I can say. So I can say x is greater than or equal to 3 in arithmetic logic. But I cannot say x plus minus equal to is equal to 3 or x plus minus equal to 3. That makes no sense. That is not an allowed sentence. Right? So there are some things that are allowed and some things that are not allowed. That is told to me by syntax. What, however, is semantics is what does it mean? What does x plus 3 mean, or what does x greater than or equal to 3 mean? And we'll talk a little bit more about this in a minute. Once we are clear with syntax and semantics, then we will get to inference procedure. So what's an inference procedure? Inference procedure is an algorithm which will spit out inferences, logical deduction. For example, x greater than or equal to 5 implies x greater than or equal to 4. Then you will get to the same notions that we have been thinking about more over and over. Is this a sound algorithm? Is this a complete algorithm? And of course, what's the complexity of this algorithm? And finally, knowledge base means a set of sentences that are known to be true in my world. Okay? And as I was saying, this notion of knowledge base is very fundamental to an agent, because any agent will be something like this. It will have a knowledge base and it will have an inference engine. Pretty much any agent will have this. Any agent you can come up with. This knowledge base will have a set of sentences in this formal language, and then you can tell the system any new concept, any new fact about the world, and then you can also ask the system to make reasonings. Ask the system whether such a fact is true in my knowledge base. For example, if you have arithmetic logic, again going back to the same example, if my knowledge base says x greater than or equal to 5, you can ask the system, can it prove x greater than or equal to 6? And the agent will say yes or no, or I can't. So now, talking specifically about logic, the syntax is the following: propositional logic. The syntax says that my atomic sentences are just variables. And then I have connectives, and the connectives are and, or, not, implies, double implication. My semantics is what is the meaning of and, what is the meaning of or, and then we will be covering these 4 inference procedures in the class today. So this is the syntax. Atoms is the starting, or you can have literals. So literals is a technical term which means either true form of a variable or the negation form of a variable, but a single variable. So P is a literal, not P is a literal, Q is a literal, but P and Q is not a literal. Okay? Sentences, any literal is a sentence. If S is a sentence, then S and S is a sentence, and S or S is a sentence. And then, and this is important, so P implies Q is nothing but a syntactic sugar for not P or Q. We should make sure that we understand this. So what does P imply Q tell me? That if P is true, then Q is true. So then it is equivalent to saying that either P is false or Q is true. Right? Because it can't happen that P is true and Q is false. So either P is false or Q is true. So this is what we have been discussing so far, that semantics and the real world have this representation barrier. So this is symbolic. The representation is symbolic. It is a representation for what is true in the world. And there are some sentences for which accordingly the semantics tells me what worlds are possible. And then as I make inferences, I can create new sentences which may also tell me, what are the equivalent facts in the world. I think this is pretty obvious. So if P and Q are two variables, then the semantics of P and Q means that both of them have to be true and everything else has to be false. Similarly here, semantics of P or Q means that any one of them can be true. So all of these three are possible worlds. This is not a possible world. Here only this is a possible world. The three are not possible.
What is world in this case?
Again, so world is, if suppose the only thing I know is P and Q, P or Q, then the worlds can be a world in which P is true, Q is true, R is false, W is false. There can be another world in which P is true, Q is false, R is true, W is true. So basically, there are a lot of the possible worlds for any assertion that I know. Does that make sense? World is what is in the reality. What we know is just the knowledge base. So what we know is only part of the reality typically. Okay, more jargon, but this is very important jargon. So, S is satisfiable if it is true in some world, any world. On the other hand, S is unsatisfiable if it is false in all worlds. Again, this notion of world is very important, so if you are confused about it, please ask now. S is valid, or the tautology, if it is true in all words. So these are exact counterparts. And this is what is the important one. S1 entails S2 whenever, if S1 is true, S2 is also true. Alright. Is this satisfiable? Yes. Anybody believes it is not satisfiable? Anybody confused about it? It is satisfiable. For example, P can be true and Q can be true, and that's a possible world for it. Is this satisfiable?
No.
Is it unsatisfiable?
Yes.
If it is not satisfiable, then it is unsatisfiable. Is this satisfiable?
Yes.
No.
S and not S can't be true at the same time. Is this satisfiable?
Always.
Is it valid or tautology?
Yes. To be or not to be.
Yes. To T or not to T. How about this? Good. Let's look at some other notation. So these are the various notations for implication. X implies Y, X doubly implies Y, X implies Y, same thing. They're just different notations. These are the more interesting ones, and probably new to you, probably. So the first notation says, with a single horizontal bar, proves. It's a notation for an algorithm, not for the reality of the world, for an algorithm. S1 proves S2 if there is this algorithm which will say S2 based on the knowledge that it had, which is S1. However, with a double bar, it is entails, and this is the truth. S1 entails S2 if wherever S1 is true, S2 is also true. Okay? So this is in the context of a knowledge of an agent. It knows some knowledge base like S1, and it wants to prove S2. That is the problem that it has. And it will have some algorithm, and if it can prove that, then that will be the proving thing. And so now let's think about soundness and completeness. What would be a sound algorithm? Imagine an algorithm that, given a knowledge base, is spitting out new things, new assertions, based on its inference process. It's proving new assertions. A sound algorithm would be,
Which is always correct.
you should raise hands. Yes.
Comes to correct inferences.
It always comes to
Always.
correct inferences. So if my algorithm says that S2 can be proved from S1, then S2 is actually entailed by S1. And what would be equivalently a complete algorithm?
They'll always find it if there's always find it.
If we without all inferences.
If the inference that I want to do is actually entailed, then it will prove it. So there will exist a proof for the all correct inferences. So I seem to have lost people here because so you have to tell me where are you confused, because I want to make sure that yes.
So what, sorry, I'm totally not clear, what's the difference between entails and implication?
Right.
If P is there, if P implies Q, then doesn't P entail Q effectively, or?
This is a syntactic symbol.
Oh, right, it's the same.
This symbol says, this symbol is used to say things about the word. So the idea is the same, the intuition is the same. So it says that if S1 is true, then S2 is also true, is the entailing, but what's happening is that this S1 is a set of knowledge, it's a set of knowledge that I have. So yeah, I mean they're semantically very similar. So I don't think you should worry about the subtle distinction. Yes?
What is improves, like algorithm says S2 from S1. What does that mean? It's not-
If the algorithm can deduce S2 from the knowledge that it had, which is S1. Yes.
So is like the difference between the proves and the entails bit mean that like if you have one algorithm that says S1 implies S2, but some other algorithm might disagree. Is that-
Here's an algorithm. It says anything is true, everything is true. Is it a sound algorithm? Is it a complete algorithm?
Yes.
It has an answer.
It is true.
Sorry? Anything, you give me any query and I'll say true, 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 true. Is it a sound algorithm? Obviously not. Is it a complete algorithm? Well, if whatever correct things you ask it, it will still say yes. Is it a useful algorithm? Probably not. But it is a complete algorithm. On the other hand, the only thing that the algorithm says yes to is for X or not X. Whenever you ask it X or not X, it will say true. Otherwise, it will not tell you anything. It will not make any implications, inferences. Will it be a sound algorithm? Will it be a complete algorithm? Heck no. Does that make sense? Yes.
I still didn't get the difference between sound. Then in the first case when you said that the algorithm always says true, why it is not sound?
Because if you ask it, X and not X, it will still say true. It will say yes, I can prove X and not X from my knowledge base. Obviously, you can't prove X and not X from any knowledge base, right?
So it means there it should be instead of prove implies entails. For sound it should be entails only if it proves.
Which is exactly the same.
Yeah, I mean, I'm exactly, but the notation. So does the implication means? I mean, instead an if, not im. If can be proved, then entails. Entails only if it can be proved. It should be.
Entails only if it can be proved.
Yeah.
No, that is the. So, if an algorithm can prove something, it will only make correct conclusions. It will only make accurate conclusions. That's the meaning of sound, intuitive, right? So a sound algorithm would be if it can prove something, it actually holds in practice. It's actually true. It is actually entailed. So for example, x greater than or equal to 5. From here we can prove that x greater than or equal to 6, right? That's an entailment. Now if I made an inference engine which given x greater than or equal to 5 could prove that x is greater than or equal to 6, then it will be a proof. I will have a proof for proving x greater than or equal to 6.
Yes, and that's what I mean, that what we have on the table for sound is that proof implies entails, but it should be the reverse. It should be entails only if there is proof.
What do you mean by only if? So entails only
So
if.
it's a subset of what's on the table.
You don't have pen here? Okay, this is a symbol for P if and only if Q, right? What is the symbol for P if Q?
Well,
Q is logic.
And what is the symbol for P only if Q?
we need two F's.
Right? And so this is the same as this. So proves implies entails.
No, because we need the arrow back, so
Sorry, well, maybe I am confused somewhere. Yeah.
So is it like entails is just a fact, like given these
Entails
things,
is the fact, and
These are true.
proof
Proof
is
is
what
a
the
derivation.
algorithm is able to
proof
do.
is a derivation.
That an algorithm is able to do.
So you can have facts, but you may not have derivations for it.
yeah, but
So that means you are not complete.
so what we have.
And whenever you have a derivation, you come up with a correct fact. That means it's
So let's think of us as intelligent beings, right? So given a new theorem, if I am able to prove it and prove it correctly, I will be a sound algorithm. Given a truth in the world, let us suppose P is equal to NP. Suppose. Or let's say P is not equal to NP. That is probably an easier thing to believe. Suppose P is not equal to NP. Am I able to prove it right now? No. So I am not a complete. There is truth somewhere. Either P is equal to NP or P is not equal to NP. Who cares? I am not a complete inference engine because I am not able to prove all things. But if I am not making a mistake, whatever I will be able to prove will be correct. It's like you wrote an exam and you got full points for it. That will be a sound agent. If you made a mistake and you proved something that is not true, then that will be an unsound agent. If you could prove everything in the world, that will be a complete agent, a complete chaos system. If there are things that you are not able to prove, that will be an incomplete chaos system. Does that make it clearer? So any algorithm, if all the things that it can prove are actually true in reality, then it's a sound algorithm. If there are things that it is not able to prove, then it's an incomplete algorithm. If it is able to prove all the things that should be proven, then it's a complete algorithm.
It's not saying all inferences are provable though, it's just saying all inferences that you have as an algorithm are provable, right? I mean,
You are asking about sound or complete? Sorry.
You're complete even if you don't know all inferences that could be made. You're complete if all the inferences that you have made are provable, right?
You are complete if all inferences that can be made are made. If there are some inferences that cannot be made, then you shouldn't prove them.
All inferences that the agent can make or that can be made by any possible agent.
All the inferences that should be made, that should be madeable,
that are possible.
that are possible in reality. I mean, the point is, here's an example. Let us suppose my agent knows this. P implies Q and P. And can I make the inference that Q is true? Okay. Can I make the inference that okay, let's suppose there is an R in the system somewhere. Can I make the inference that R is true? Okay. So there is an algorithm which can prove that Q is true and also proves that R is true. Here is an algorithm that proves that Q is true. Here is an algorithm that proves that not Q is true and R is true and Q is true. Is this a sound agent? Sound inference algorithm?
Yes.
Is it sound?
Yes.
Given information.
The first agent says that Q is true and R is true. First algorithm. Is it sound? Is R true?
No.
We can't say R may be true, but we can't prove it, right?
You say it might be sound or it might not be sound then?
No, it's unsound.
So this is exactly unsound algorithm because it is making inferences that should not be made. This and all reasonable versions of it like Q or Q, P or Q, and so on. Suppose it spits all of these, then this will be a complete algorithm and also sound algorithm. And suppose this one says all things possible. Then this will be an unsound algorithm, but complete. Not useful again. Unsound and complete is not interesting. I'm just telling you for completeness. Sound is the important part. We should not make incorrect deductions. Is the part about being sound.
So complete algorithm can make incorrect assumptions.
If it is unsound. If it is unsound. So the intuition here is all truth and nothing but the truth is what we want, really. Now think about you are going as a witness and the judge asks you, please, say that you will speak all truth and nothing but the truth. That is not possible really because the guy cannot say all truths. The guy may not know about quantum mechanics or may not know about, things that he doesn't know. So really what the judge wants to make sure is that he's going to be telling nothing but the truth, and that will be the sound procedure, that will be the sound witness. A complete witness, if he could tell all truth, would be sort of like God. Yes?
These are relative to your knowledge base.
Yeah, so that's a great point. So,
You have a complete.
good point. So, okay, you're right. So, by saying that all truth is nothing but the truth, the judge wants to make sure that whatever assertions he can make from his knowledge base, he should be making them when asked. Great point. Thank you. All right, let's move forward. So, there are two problems that we will be studying. One is called model finding and one is called deduction. Deduction is given a question, I want to prove that it can be proven. I want to prove that question. And model finding on the other hand says, give me background knowledge and I want to prove that I can find a world in which this formula holds. Okay? So model finding is sort of like a constraint satisfaction problem. I want to find a world. This on the other hand is an inference problem, and there are two approaches that we are going to study. One is called contradiction and one is called modus ponens. And I think we already have seen a couple of these. One of these at least. There are specific syntactic forms which are interesting for us. One of the syntactic forms, so the general logic is where you can put all of these things together, like any sentence with any sentence and so on. Then there are specific forms that people have studied, like conjunctive normal form. Conjunctive normal form, conjunction normal form. It will be very important to us, CNF. So the idea there is that I have a conjunction of disjunctions. And each disjunction is called a clause. Okay? So in this particular case, one clause is not Q or S, and another clause is not S or not T. And so we will use a set notation again and again, where each clause will be mentioned as a comma separated list. Okay. And then there will be a set of those. And an empty clause will be a clause where there is nothing in it. And what's the disjunction of an empty clause? It's false. So, whenever we see empty clause, that means we have found false. Something is wrong, this is not consistent. This is an important form because any formula can be converted into a CNF.
False and not the empty set.
Empty set is always true because empty set says I have nothing. No, it's vacuously true.
But an empty clause is not the same as the empty set.
No, and we will see examples of why that is.
This sounds more like philosophy than computer science.
We will get there. So, yeah. Then we can talk about binary clauses, which have only two literals. Then another special kind of logic happens when you have horn clauses. Horn clauses are clauses which are all positive. On the left side is a conjunction of positive literals, and on the right side of the implication is a single positive literal. So this can be equivalently converted into a clause which has all negations and one positive literal. So Q and R implies S gets converted into not Q or not R or S. Do all of you see how that happens? This implies this is not antecedent or consequent. Not Q and R by De Morgan's law becomes not Q or not R. Alright, so let's get to the algorithms, and this is the goal. We'll first do forward chaining, then we will do resolution, and then we will do Davis-Putnam, and then walk-side. That's the plan. Okay. The inference procedure is a mechanical process for computing new sentences that are true and that are consistent with my knowledge base, right, as we have been discussing. So, the first mechanism is called forward checking or forward chaining, and that's based on the rule of modus ponens. So again, modus ponens is this rule which says if P implies Q and P is true, then Q is implied. That's the rule. Or if P1 and P2 and so on and Pn implies Q and we know P1 and P2 and Pn to be true, then we can conclude Q. That's forward chain. There is an equivalent version of this called backward search. Let's talk about it in a minute. So, as we had bidirectional search, right? So we could do forward search in forward direction. We can do search in backward direction. This is the same. This is search in forward direction, and this is search in backward direction. But we'll focus on forward, so because you know the concepts by now. All right. Here is a way to test whether you understood this right or not. If this is the only rule you were allowed to use, anything that you conclude is using this rule. Will such an algorithm be a sound algorithm?
Yes.
Anybody has any issues with that? You're fine? Now, will it be a complete algorithm?
No.
Okay, who believes it will not be a complete algorithm? Why not? So if it cannot be provable in the reality, then it should not be provable by a complete algorithm. So the question is, if it can be proved, if it is true in reality, but I can't prove it by my algorithm, then it will be an incomplete algorithm. So can you think of something which is true in reality, but this algorithm will not be able to prove it?
Or anything other than Q?
But we may not know that it is true in reality. with every knowledge base, think of the possible words that it is consistent with. I think actually this is the intuition that we are missing.
Oh,
With-
well, there, Q,
Yeah.
there may be places where Q is true and all the P's don't.
No. Think of all the words that are possible. Remove all words that are inconsistent with what we already know. Okay?
Which is P. Right?
Sorry?
What we already know is P.
No, we know P implies Q and P.
That's what we know.
P is true or false? What do you know?
P is true.
Yeah,
P is true.
That's my question.
Oh,
Well,
sorry.
what's our universal set of letters?
I don't know, too much.
P is false and Q is false, we can't prove that, because that might be true in this world, but we can't prove it.
P is false and Q is false.
I'm thinking something different, sorry. I was thinking just P implies Q.
You were very close, yeah.
If you have P implies Q and you have not Q, you've got not P, but you can't get there just with this rule.
Exactly. I think you got the correct, one of the good examples. So you have P implies Q and you have not Q. So this means that P should be false, right?
Yes.
Yes. Number is still nice.
Yeah. Right? With just modest ponens, can you prove this? The only rule you are allowed to use is that if P implies Q and P is true, then I can prove Q. That is the only rule you are allowed to use. Using just this rule, can you prove not P to be false? Or not P to be true or P to be false? No, you can't. So this is an example of a situation where there is truth, there is reality. In reality, this is true. So P implies Q, comma not Q, entails not P, but P implies Q, comma not Q, cannot prove not P using just the forward chaining algorithm that we talked about. So, right, so I was talking about the intuition that we are missing. See, the intuition is the following. We have some knowledge base. In this knowledge base, right, and then we have a possible set of words. So suppose the only symbols in my knowledge base are P and Q, then how many words can I be in? I can be in 4 words, right? There will be some set of words which will be consistent with my knowledge base. Right? What is entailed is a sentence that is true in all of those words. That is the truth. Right? For example, suppose the only thing I know is P and Q. This is the only thing I know. Okay? Let us suppose we have 4 words. The 4 words are true, true, false, 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 true, true, false, true, true, right? These are the only possible 4 words. How many of these are consistent with my knowledge base? Just 1. This is the only word that is consistent with my knowledge base. Now, suppose I am asked, is P true? Is P true entailed by my knowledge base?
Yes.
Can modest ponens prove it? Modest ponens can't prove it. Right? Although forward checking can prove it, so we'll just talk about that in a minute. Similarly, if my knowledge base says P or Q, now I have 3 words which are possible. All of these 3 words are now possible. And now I could ask a question if it holds, there's no other question with just two variables, so it's hard, but that could hold in both of these, all three of these words, then that will be an entailed sentence. Okay. Lots of examples. So, so we realize that it's a sound procedure. Whatever we will be able to prove will be correct, but it is not complete. And here's another example, different from what Kim gave us. Is this always true? Right? This is entailed by nothing. But obviously, forward checking will not be able to prove it. Here's a fun fact. If my knowledge base has only horn clauses and the query is a single literal, then forward checking is actually complete. So it's a reduction of the possible space that I am dealing with, but that's alright. There are situations where you have mostly horn clauses or only horn clauses, and if that is true, and if I'm talking about single literal queries, then it's a polynomial size, in fact linear procedure, which will always tell me all possible inferences. That's pretty awesome. Yes?
What's the difference between forward chaining and modus ponens?
Right, so let's discuss forward chaining exactly, and so we will know exactly how it works. Modus ponens is the rule on which forward chaining is based. So, this is the algorithm. The algorithm is actually that simple. I mean, really, it's a trivial algorithm. So, suppose this is my knowledge base. Then I will create this graph. And this graph says, represent my knowledge in this graph. So, for example, this is a representation for A and B, and whenever A and B is true, it implies L. This is a representation for L and B, and whenever L and B is true, it implies M, and so on. So the algorithm says, okay, with each of these points, just remember how many edges are coming in, and keep a count on how many of those I still do not know to be true. So suppose here I know A and B to be true. So I say, alright, let me put this in the knowledge base. So I put A to be true. I propagated this information forward, which means this now has only one parent which is not satisfied. This also has only one parent which is not satisfied. Then I put B in. Now this has no parents which are not satisfied. So now I can deduce something. What can I deduce? Exactly. A and B is both true. I can deduce L. So I send this information forward and put it in the queue. Now I remove L from the queue. So what happens? This becomes 0. That means now I can deduce M. And moreover, one of the counts get reduced here. Keep moving. So put M in the queue. Remove M from the queue. Send this information forward. Now we have 0. As soon as we have 0, we move forward and we put this in the queue. Now when we have removed this from the queue, then this also will become 0, this also will become 0. So move forward, you got this in the queue. And remove this from the queue, you have proved Q, which is what we wanted to do, for example. So very simple procedure.
I have a question. Can you go back to where A and B were true? So, okay, A and B you put true, so that one becomes 0, and that one becomes 1. Then what happens with L? What can you conclude about L?
Whenever there is the antecedents are both satisfied, then you can prove the consequent, right? If you know that A and B implies L and A and B are both true, then we can know L. So that means we created this L and we put it in the queue. We now know that this can be satisfied.
This is forward chain?
This is forward chain. Any other questions on the algorithm? The algorithm is yes. Harun, right?
Yes.
Yes.
So after doing this, so this is kind of our state or inference engine, and now we would be able to answer questions.
Yes, so if I asked you, is Q true? You will say, wait. Let me run this procedure. If I could get Q from my procedure, then yes, it is true. If you ask me, is B and L true? You will say, let me try, but there is no way to generate conjunctions, right, in this case. So this system will naturally say, I don't know.
But it knows that B is true
And L is true, but it doesn't know the rule that if B is true and L is true independently, then you can conclude B and L, because that is not the rule that we gave it. Then you can put it as a post processor. But if I asked it, is Q or not Q true, then it will have no idea. Right? Okay.
So if you ask is L true, it will be yes.
If you ask is L true, it will say yes. If you ask is M true, it will give yes. All of those things. Good. This is also data-driven reasoning. You are starting from the data, and then you are doing inference on top of it, irrespective of what you wanted to prove or answer. But if you started from what you wanted to prove and went backwards, that will be backward chaining. So it's exactly this. You know, if you remember the old story about Watson and Holmes that we discussed in the very first lecture, about Holmes starting asking Watson, what do you see, and Watson starting to make lots of inferences. That will be forward chaining. But knowing that my tent is gone, and going back from there and proving that would be backward chaining. So forward chaining has this problem that it just keeps spitting out inferences without any idea of what is important. All right. Let's do resolution, and then we'll take a quick break. Resolution is proof by contradiction. But before we do resolution, let me do a quick study of how to convert any formula into CNF. This will be very important for you, even for your assignment. So suppose this is the formula that I wanted to convert to CNF. So CNF is a conjunction of disjunctions. So first of all, I will eliminate the double implication. So A doubly implies B means A implies B and B implies A. Right? So in this case, we will say this one implies this, and this one implies this. Next, we will remove any implication with P implies Q is equal to not P or Q. So we will say not of this or this, and not of this bigger parenthetical term or this. Now, is this already a clause? Yes. Because we are only allowing disjunctions in a clause. This is already a clause, this is disjunctions. So far so good. Now our goal is to convert this into a CNF form also. So not A or B, you can apply De Morgan's law. So not A or B becomes not A and not B. So this becomes not P12 and not P21. Now we have a conjunction and a disjunction. So we can use distribution law, right? So you can distribute this, so we will get this term or this term and not P21 or B11. This is a clause, this is a clause, this is a clause. So now we have got our CNF. So this will be very simple. I mean, this is old Boolean algebra, but these are the basic rules that you will apply in approximately in this order, and it will keep working out. All right. Now resolution basically says the following. So it is again a rule, single rule that we are going to use. And the rule says, if I have a clause with P in it and another clause with not P in it, then I can prove this thing. I can prove that if P or alpha is true, or not P or beta or gamma is true, then I can prove that alpha or beta or gamma has to be true. Intuitively, can you see why that is going to happen? So either P is true, in which case this not P is not going to be contributing, so one of beta or gamma have to be true, or P is false, in which case this P is not going to be contributing and alpha has to be true. So therefore, we can prove alpha or beta. So P or anything not P or anything, we can prove that anything 1 or anything 2. That's called resolution. Studied in 65. It is developed in 65. There is a very interesting property of resolution. The property is, of course, it is sound because we just intuitively proved it. Which means if I can prove this, it will be true in all the worlds. But the second property, which is pretty awesome about resolution, is that if a knowledge base is unsatisfiable, that means if a knowledge base cannot happen in reality, which means there is no model in the world that is consistent with all the sentences in my knowledge base, then resolution will come up with an empty clause. And as soon as it comes up with an empty clause, that's false. We have proven something. So basically, that's a rule. That's a theorem that if S is unsatisfiable, then by applying resolution, we will always be able to derive empty clause. You have a question?
Yeah, can you elaborate on that a little bit? I'm not clear on completeness or, sorry, refutation.
Refutation completeness says that if a formula is unsatisfiable, then my algorithm will always be able to refute it.
So, just what would be unsatisfiable if the variable?
P and not P is an unsatisfiable formula, for example. And we'll just show an example. The first thing I want to show is that modus ponens is actually a special case of resolution. But the first step to start to resolution is to convert everything in a CNF formula, because I am starting with clauses, right? So what will be a conversion for CNF formula? A or B can be converted into not A or B. A implies B can be converted into not A or B. So this is the first thing I know. The second thing I know is that A is true, right? Now if I did resolution on these two clauses, what will I get? Right? Because this is not P or alpha and this is P or nothing, so beta, and then you do resolution, you got B. So it's actually a modus ponens is a special case of resolution. Pretty awesome. Okay. Now, this is a very interesting example. This shows that resolution is not complete. It is refutation complete but not complete otherwise. So here are 3 sentences. If Will goes, Jane will go. If Will does not go, Jane will go. Now you and I, can we conclude that Jane is always going to go? Let's see if resolution can conclude this. Okay? So we can resolve these two, and what will we get? J or J. That's it. From J or J, you and I know that we will get J, but resolution does not. It's silly. So it's a silly example that we are not going to be able to get J from it, but you will have to put in more post-processing on top of it in order to get J. However, we can prove the same thing using contradiction. So if I gave you this and I asked you to prove using contradiction, what would you do? You will assume something. You will assume that, let us suppose Jane does not go. And then you will derive a contradiction somewhere. Right? So let's do that. So if we assume the 3 things now, not W or J, not J, then with these 2 we can derive not W. With these 2 we can derive J, and with these 2 we can derive false. So we can prove. Let's take a better example. That will give you the power of resolution. You have a question? Yeah. If the unicorn is mythical, then it is immortal. But if it is not mythical, it is a mammal. If the unicorn is either immortal or a mammal, then it is hard. Prove that the unicorn is hard. I'm sure that if you have studied logic before, you would have had to do these kinds of problems. But we'll try to do this using resolution. So the first step of starting to answer these questions is to create symbols, right? So let us create symbols. So what should we create a symbol for? Mythical M, immortal I, mammal A, and horn. Okay, what do we know in our database, in our knowledge base? Mythical implies immortal. Represented as a clause, it is not M or I. Not M implies A, that means M or A, and so on. We got these. This is my knowledge base. Now the query is I have to prove H. Using resolution, what will we start with? Using resolution. So if I have to prove H, what will we start with? We want to refute it. So we start with the contradiction, which is not H. Now I want to prove false. This should not hold together. Let's prove false. We can, do resolution here. So H goes away, we got not A. H goes away, we got not I. We can do resolution here. So we can get M. We can get not M. We can do resolution here. We got an empty class.
Okay. That's why empty has to be false. So the rules work.
All right. Let's skip the discussion on how do we implement resolution. It's interesting. In fact, in order to implement resolution, you have to do search of some kind. So to think about the search space, the operator space, heuristics. Let's skip that discussion. And we'll take a quick break. And when we return, we'll talk about model finding, which is how do we find the assignments to variables. Okay. So we will study the next problem. So up until now we were making inferences and we were asking the question, is this inference true or not true? Now we'll work on a different problem which is called model finding. So we have established already that given a knowledge base, there can be many possible words that are consistent with their knowledge base. So if I have a knowledge base of n variables, then there are total possible 2 to the power n words, and some of those words will be consistent with the semantics of the sentences that are true in my knowledge base. We have established that hopefully by now. Now the question that we are asking is, give me any one word that satisfies this knowledge base. Give me any one model that satisfies this knowledge base. So what does that mean? Find assignments to variables that makes this knowledge base true. Any one assignment, any one of these rows. Okay? And now let us see that it's a CSP. Why is this a CSP? We have variables, which are the n variables in my domain. We have values. What are the possible values? True and false for each variable. We have constraints. What are the constraints? Suppose my SAT formula is given to me as a CNF. Then each clause is a constraint. If my clause says A or B or C, that's a constraint. I can't have both A, B and C false. That's it. So it's a CSP. So in some sense, a SAT formula, a SAT problem is a subset of CSP. We will also show the reverse direction in some time, that any CSP can be converted into a SAT. Now, what is the dumbest way to solve this problem? Try every possible assignment, and it's called model enumeration, obviously. And if you can find anyone, return it. If you can't find anyone after this, return unsatisfied. Okay. Now we already know about a method to solve CSPs which was better than brute force, which was answer to all good questions is help planning with random research. No, so I was talking about most of the class that we had last time, which was a systematic search. So what's a systematic search algorithm that we have already worked on last time? It's called backtracking search. The name is less important, but I think you remember the idea of take one variable, assign it a value, move forward, take another variable, assign it a value. And so in the context of logic, that algorithm is called DPLL. For no good reason but the fact that the inventors were Davis, Putnam, Loveland and Logan. And what we are going to do is that we are going to do the DPLL algorithm and also have more constraint propagation for satisfiability to make this a complete algorithm. So here's the starting point, which makes a lot of sense hopefully to you by now already. If we are already at a node where f is false, return false. If we are already at a node that makes f true, return true. Otherwise, choose any variable p in this formula which has not been assigned so far and recursively search for the direction p equal to 0 and the direction p equal to 1 and hopefully one of them will return a true assignment.
What is P? Partial assignment.
P is a partial assignment. Okay? This is just saying pick a variable, assign a value, search, 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 come back, keep backtracking and eventually do the search tree. One variable at a time. And of course we will add all the intuition that we added last time. But let's just make sure that we understand this algorithm. So here's our knowledge base. And we want to, or now I'm going to call it a SAT formula. So to make things, go away from the knowledge representation side of things and get into the more practical side of things, the constraint reasoning side of things. So we have a SAT formula, which is a conjunction of these clauses. So let us suppose we pick A first, assign it false, pick B, assign it false, pick C, assign it false, and now see that all the formulas are satisfied. Are all the formulas satisfied? Not the first one. So we backtrack, try to assign C to be true, and keep doing this, and at some point we will find our satisfying assignment, probably here, which is A true, B false, C true. A true, B false, C true. So it's a search algorithm, backtracking search. In some sense, the search space is partial assignments, and the algorithm is like depth first. Yeah, you can have multiple solutions, so you stop whenever you find one, because you just need one. That's the goal. It's like in constraint satisfaction, you can have multiple solutions. You stop when you find one satisfying assignment. It's the same problem we are studying in some sense. Now we're going to add some intuitions that are logic specific that make it solve faster, that make DPLL faster. Any ideas? Let's go back to this, what we were doing one at a time. Should I try? I guess I could try B false. At this point, should I try C false? Why not?
If it's false, there's no way that first constraint can be true.
Because there is no way this first constraint can be true. If I have a clause with only one literal remaining, everything else is false, I need to set it to that literal to be true. If the clause is C, then I have to set it C to be true. If the clause is not C, I have to set C to be false. Yes?
Your first and third clauses are contradictory.
No.
At this point.
At this point, yeah. Yeah, so that's we would have to realize it at some point, maybe right here. So another thing that I missed out. At this point, does this clause matter? Does this clause matter? I'm wasting my time, doing things with it. They should just go, because they have already been set true. So these are the two intuitions that we are going to add. The first intuition is, it is okay to delete clause that have any one true literal. And second, it is important to shorten clauses that contain false literals. And then so I ran ahead of myself, unfortunately. So the last thing is that if we get empty clause, that means we have achieved false. So let's see what that means. So first we are going to remove the clauses that contain a true literal. If the formula contains no clauses, then we will say it's true because it's vacuously true. If a formula contains an empty clause, then we have found it early, and we will say false, or not early necessarily. And if it contains a not literal, then we are going to remove it and shorten it. So I think it's just basic implementation. We haven't done the exciting part yet, and I ran ahead of myself. So which means that if I set it to false, I get rid of this, get rid of this, get rid of this, get rid of this clause completely, because this clause is now satisfied. So this is what I commit with, right? B or C, F or B or C becomes B or C, F or not B becomes not B, F or not C becomes not C, and T true or C is not important. Keep going. So I said B to be false, get rid of this, reduce this. Set C to be false, this is get a contradiction because of the empty clause. Now we are going to add more things that I started talking about. So the thing that I mentioned is unit literals, which says if there is a clause with only one literal in it, set it right there. Don't wait for some later assignment to set it, because I now already know what its value should be under the previous assignment. So now notice what happens with unit. This is called unit propagation. Okay. Notice what happens with unit propagation. I have to set C to be false. As soon as I set C to be false, what happens?
It's eliminated from the first clause.
It is eliminated from the first clause. Now, with unit propagation, what will I have to set? B false. As soon as I set B false, what happens? So now I have to set D to be true. And as soon as I set D to be true, this clause is gone. So basically, I am left with just D. Interesting.
Not be as true.
As soon as I set C to be false, this was also satisfied.
Why you said literally false?
Because I wanted to satisfy this. So basically, just this notion of unit resolution, unit propagation gets me a lot of the way already. Now I know what to do, set D to be true, and I'm done. So basically I solved my problem. Tyson.
Yeah, but in implementation, wouldn't the cost of this kind of checking potentially be almost as expensive as just plugging in?
Not at all. Because keeping track of unit literals is actually very easy. You have a set of clauses, and you have to just keep track of how many literals are remaining in that clause, and as soon as there's only one, you say, okay, propagate. Go over. See, that's the input size, right? So it's
Ordering.
Okay, so it's just gonna take more space because you're gonna have to keep track of all these extra literals that you wouldn't have to keep track of otherwise. How long? Well,
yeah,
depends on
you can also, it depends on the implementation. Because your input is still the SAT formula, so that much input you have got, and you are only reducing the size. So you can, as you right? So you can keep reducing the size. So then when you backtrack, you will have to access the original formula and do some changes. But I don't think space is an issue because we are doing depth first search. So because we are doing depth first search, we can keep adding little bits of memory for each layer because we are not keeping a full frontier exponential size memory. It's only a one path down the thing and then back. Backtracking. So space is irrelevant if you are doing backtracking search. Okay, so the second interesting yes.
Why didn't we keep a E?
Because as soon as we set C to false, this formula is this clause is satisfied. So we don't need this clause anymore. That's the previous intuition, right? As soon as we set something to true, it goes away. If we set something to false, it's removed from the clause. If we set something to true, then the clause goes away because that clause is now satisfied. It's no longer a constraint under the current partial assignment. Okay, pure literals. This is very interesting. It's actually very valuable. It says, if a symbol always appears with the same sign, set that literal to true. So for example, look at this. D here always appears only in a true mode. So an easy way to do this is to set it to true, because by setting it to false I am not gaining anything. But by setting it to true I am gaining something.
Set it to false, you can eliminate just the literal. If you set it to true, you can eliminate all clauses.
Exactly.
But can it happen that the solution is should be set to false?
You may have some solutions where D is set to false, but you are guaranteed to have a solution where D is set to true.
But can't you have solutions only when D is set to false?
Of course not.
Because we're in C and F.
So,
Because there is no clause where D is false.
because there is no clause where D is false, so you are not gaining anything by setting. And by the way, this you can do as search is happening. So based on the partial assignment, some clauses will go away, and now more literals will become pure literals. Just propagate that information forward. So you're reducing your search by doing some simplifications. So this is similar to constraint propagation in some sense, forward checking, and things that we discussed last time. It's pretty similar to forward checking. Unit propagation is same as forward checking, for example. So now we add these two. So if F contains a unit clause or a pure literal, then you just quickly set it to that value and move forward. You don't need to do the other side. And this is the DPLL algorithm. Question, Anita? That all the clauses got satisfied, so they got removed. Kept getting removed. Paul?
I understand that a unit literal will, it will make the whole formula true or false, but if you have a pure literal, that doesn't, it's faster to set it to one or the other.
You are not missing any, you are not missing the, you are not making, you will always, if there is a solution,
Okay.
at this point, by setting it to true, you will still find that solution, or a solution.
Okay.
You're guaranteed to find a
You are
solution.
guaranteed to find a solution. So if there is a solution in the subtree, then by setting it to just one branch, you are still guaranteed to find that solution, a solution.
Can you help us understand why you have that guarantee?
Yes, because let's see. Let us create a knowledge base. In fact, let us take exactly that knowledge base that we had. This is my knowledge base. Tell me, D can be false. But by setting D to false, by setting D to true, I am making some clauses true and not hurting any other clause. Do you see that? By setting D to true, am I hurting this clause? I am not changing anything here. I'm not changing anything in this third clause, I'm not changing anything in the fifth clause. And by setting D to true, I am making this clause true and this clause true. So this is only benefit, there is no loss here. If there was a solution, you will get it. Okay? So this is my DPLL for there. Even if it goes down the false branch, when it backtracks, it will get to the true branch directly. Why? So let's say we decide on A to be false, so we get B or C, not B, not C, and this clause goes away. Now as soon as we have not B, we can set B to false. As soon as we have not C, we can set C to false. We make this formula unsatisfiable. We go back, we had not done any search, we had just gone one branch, so we move further up, set A to true. As soon as we set A to true, this is gone, this is gone, this is gone. What we are left with is C. It's a pure literal or unit literal. Either way, we set C to true and we are done. So this is the actual search that happens in this knowledge base. And now the last question: where could we use a heuristic to further improve our performance?
Things like minimum remaining values.
So what are we missing? We are missing a heuristic to pick the variable and a heuristic to pick the value.
I was gonna say that you could probably pick the variable that has the most similar values, so the most true to the most false.
Yeah, so, but you see that this is the only thing that we are missing. We have created a search procedure, and the other thing that we have learned in the course is that search is great, but you have to direct the search somehow or the other, so now we have to direct the search. That's the last point, to use heuristics. So now we have been talking about this idea of most constraint variable. Now in CSPs, what was our notion of most constraint variable?
Which appears in most clauses.
No. There was a first idea before that, which was minimum remaining values. Yes, minimum remaining value makes sense in SAT formula.
You can have at most two values.
You can have at most two values, and if it is not pure or something, it will have two values. So it will exactly have two values. So we have to use the other notion. So the other notion is use a variable that appears in most clauses is the suggestion. That's fine, but there is another intuition that we can add. See, we have put on top of it a very fast procedure to propagate information. So if we had some variable that created more unit clauses, then that will be really awesome, right? Because all those unit clauses will just rush quickly and we will not have to do much search. So now the heuristic becomes sure, the most constraint variable, but at the same time one that aids in our inference process, the part of the inference, the propagation, the constraint propagation that we have developed. So the heuristic is called Mausam heuristic, and it is most occurrences in the clauses of minimum length. So if I have binary clauses, then I would prefer to search, pick that variable which creates, say, many unit clauses, because these unit clauses are going to be extremely helpful. We will just propagate information forward. Yes.
Can we generalize that further and use, say, having the smallest average size of a clause that it's in, or is it only going to work for most occurrences of that very small clause? Like, is a variable that's in a clause of size 3 better than a variable in a clause of size 4?
The variable which is in the clause of size 3 is probably better than the variable which is in the clause of size 4, but you will not have any clause of size 3. So your heuristic should be general enough to handle different clauses. So that's why it says most occurrences in the clauses of minimum length. So if you have some clauses which are minimum length, which are very small length, then you should just make them unit clauses and propagate this information forward, and that will be helpful. So this part should have been easier relatively because it is building upon the previous weeks. So DPLL has been an immensely successful algorithm. It was invented in 1962. By 1992 we had implementations which could do 300 propositions. This was slowly improving, but now, okay, and then this is what I'm going to do next, is to tell you that really what has happened today is that the SAT solvers have become immensely powerful. Okay? Immensely powerful. And so in the rest of the class, and we still have time, so I'm hoping that I'll still be able to get there, is to tell you A, why is this important, how will this SAT can be used, and 2, tell you some of the advanced techniques that people have developed over the last 5 to 10 years. That's the goal for today. Let's see how much we're able to cover it.